everyone, in this video we are going to talk about the dimensionality reduction with principal component analysis. So what is dimensionality reduction? So there are dimension of an m cross n matrix and let that matrix be our database itself, right? So the number there can be many columns. I told you there are x and y values. There is one value of y, and that we are going to predict, that our machine learning model is going to predict that value, and the remaining values are the x values which we are going to feed. So the number of x values gives us the dimension of our database, right? So how can we reduce the dimensions? Of course, if the number of dimension is quite more, then our time complexity will be much more, right? So we always would want to reduce our dimensions. So how can we do that? One basic way can be to imagine that, suppose y is the price of a house, x is the length, and x1 is the length, one feature, and x2 is, suppose, breadth, the two features. So we can easily say that we can remove those two columns of length and breadth and replace it by area, right? We can easily do that because we know that the price of a house will be related to area only. So two dimensions, we have reduced it to one dimension. Now our machine learning model will execute its the internal process is quite fast, quite, it will be very quick. So this is known as dimensionality reduction. This was just the basics. We are going to see some of the most advanced forms of it. So let us just start. So by the end of this video, you will be able to understand eigen decomposition and eigenvalues of a matrix. You need to know this to understand the mathematics behind it, and uh, understand dimensionality reduction. Principal component analysis is nothing but one of the method to do dimensionality reduction, and understand correlation matrix along with mathematics behind it. So let's see what is eigen decomposition. I had explained it in my mathematics for machine learning video. You can find the link in the description, or you just focus now that an eigenvector of a square matrix A is a non-zero vector V such that the multiplication with A changes only the scale of V. So there is a vector V and there is a matrix A, or we can represent a vector also by a matrix. I had told you this earlier also. If you do the dot product, it will just change the length of the length of the vector v and nothing else. Well, then we can say that k is the eigenvalue corresponding to the eigenvector. V is the eigenvector, A is our reference matrix, K is the eigenvalue. If A is a set of eigenvalues v1, v2 represented by matrix V, then the corresponding eigenvalues lambda1, lambda2 represented by vector lambda, then the eigen decomposition is given by. So what is eigen decomposition? See, you know factorization, right? We have done factorization. Let's say do factorization of 100. What will be your answer? 5 square into 2 square. So this is nothing but a type of factorization, you can say. There's a matrix, we can break the matrix into its components in this way. What are the components? The components are eigenvectors and eigenvalues, similar, which correspond to the similarity like factors, right? So what I have done, basically I have basically multiplied it by V inverse on both the sides. So you see V inverse, and if you do a little bit of math, you can easily get it like diagonal of lambda is matrix, lambda 1, lambda 2 are the diagonal elements, and the remaining all the elements are 0. So basically you are multiplying each elements of V with lambda 1, lambda 2, v1 lambda 1, v2 lambda 2. The matrix will come this way and you multiply it with V inverse. You do a little bit of pen and paper, you will easily get this matrix. So what have we basically done? I told you lambda 1 v1 and lambda 2 v2 is going to come if you do the mathematics. Then so you see, before multiplication, let this be two perpendicular vectors. So after multiplication they make ellipse, right? I told you that eigenvector only changes the scale of the vector v, right? So dimension reduction with PCA, I told you what is about dimension reduction earlier in this video. And principal component analysis, it is the specific technique for dimension reduction, and it also helps in arriving at better visualization models. So let's understand this very clearly. We are plotting, let's say, two factors x and y on the graph. What we find, let's x be the skill of flying of an RC remote control helicopter, and you know that RC remote control helicopter are not too easy to fly, and it is not very obvious like toys. Like if you, even if you take drones, you need to understand the mechanism to which like for a quadrocopter drone, which to the airframe, in the airframe, the which two um, fans you gonna slow down and which two you gonna speed up, then your uh, helicopter will go which way, you need to understand that. So let us plot skill of flying a helicopter, and on the y-axis enjoyment, right, how much I am enjoying to fly it. So by common sense we can easily say that the amount of enjoyment I will get to fly, the better will be my skill. This is true in most of the case. If you are enjoying machine learning while studying, you will understand it better, right? So it is true in every case. So you see, the graph will be something like this, and let us define it, the earlier the features were x1 and x2. Let us define now new features u1 and u2, where they are u1 is let's assume it to be the best line fit of this, and u2 be the perpendicular to this. Now you see the noise along u2 is very negligible, and most of our data lies along u1. So even if we ignore the u2 dimension, does it matter at all? No, it will matter at all. I cannot say it won't matter, but little bit it would matter, and that much sacrifice we are willing to do. So when two factors x1 and x2 are correlated, most of the data lies along the u1, making it the principal component. u1 is our principal component. Hence we can safely work with u1 alone and discard u2 dimension. So what we will do, we have some n dimension x1, x2, xn on our database, which are the columns basically of x. So two of the dimension may be related to each other. We can find that by correlation matrix, which I am going to discuss. So if two skills and if two features are correlated to each other, then we can plot the graph of them and find some vector to be neglected, along which the noise is very less. We can say the noise is very less along u2. So our 2D problem now becomes a 1D problem, and hence we have reduced one dimension in our dataset. So I told you about the correlation matrix. See, this thing you need to understand first. The length of projection of x on a unit vector u is given by x transpose u. This also represents the distance of projection of x from the origin. What is this exactly? What is x? What is u? This each point is our x. Each of the points is our x, right? And u, I told you what is u. This is our only u component along this. So let u be the unit vector along u2. Let u be the unit vector along u2. Vector, by vector mechanics, you know that what is the length of something along a direction. We take the dot product, right? For example, if we tell 3 I cap, what does it means? 3 I hat or 3 I cap, if we tell, what does it means? It means that 3 units along unit of x-axis, along the unit vector of x. So 3 dot I. So similarly, u is the unit vector along this. So x transpose dot u. Now what is x transpose? Why I have taken transpose? See, this is two similar matrix. This will be we can represent a vector by matrix. I have told this to I have explained this many times. So what will be these two matrices? Suppose this is I cross j matrix. This is also I cross j matrix. Can you multiply those two? You tell me, can you multiply I cross j and I cross j matrix? No, you can't. Because you know, if one matrix is of form I cross j, to multiply with the another matrix by its side, it should be j cross k. Right? The number of you can say the columns of the first matrix must be equal to the number of rows of the second matrix. Then you can multiply two matrices, right? So that's why we do X transpose. We are not changing the inside elements of X. We are just changing the making it transpose so that we can multiply it. Because after all, it is a vector which we are represented it by a matrix, right? So this is the essence behind it, X transpose U. So this also represents the distance of the projection Fx from the U, right? So from X, how much is the distance? P is X transpose U. Now we are going to calculate MSE, mean squared error. From this, how much is the distance? X transpose U, there are I points. I told you X is each point, so there are, let's say there are ith point, and there are total of m points. So 1 by m summation, this is the mean square error. So you see, it is quite simple. I have just taken the squared of each term and then sum it and divide it by total number of terms, which is mean squared error, right? Then to multiply this, I have told you again why I won't write u into u, and means I would prefer writing u into u transpose, right? We can do that. So we write it in this way. And what is u and u transpose? Does it anything have to do with the summation? No. So we can easily take it out. So u and u transpose can be taken out, and this is a specific kind of matrix which we tell as the covariance or correlation matrix, which is nothing but this x1 and x2. If x1 is identical to x1, right? So the correlation score is high, 1. So we give it 1. If x1 x2 is equal to x2, so in this we write x1, and you see x1 with x2 the relation is 0.8, means some amount of relation it is having. X2 with x1 also it will be 0.8. So if it is correlation score is 1, it is completely correlated. No means not at all correlated. So the dimension reduction is applied when the correlation score is high. So first we will calculate the machine will calculate the correlation score. If it is high, then it will decide whether to apply the dimensionality reduction or not. Generalization: if you wish to project some n-dimensional data into the k-dimensional subspace, what I showed you earlier was two dimensions, u1 and u2, along which the noise was less along one. So we reduced two dimension into one dimensions. But in general, if you wish to project n-dimensional data into k-dimensional subspace where k is less than n, we decompose the covariance matrix into eigenvectors and eigenvalues. I showed it in the first slide probably, how to break a matrix into eigenvectors and eigenvalues, just like the factors. Then we select top k eigenvectors from the list. Top k means whose weightage is maximum, right? The top k eigenvectors are those which have the largest k or largest eigenvectors. So how we'll understand the k largest eigenvectors? From the correlation matrix we are going to understand this. This way, dimensional reduction is carried out in general by the computer. We may not remember the exact process along with the formulas in the long run, right? If you are going to be an AI developer, you don't need to remember all the formulas, but you need to understand outline of what is happening in the background. What is the machine doing? If I write this code, these things you need to do, right? You can't completely mug up things. So some applications of PA include data compression and noise reduction. So yeah, that's all from this video. Meet you in the next video about this principal component analysis, and we will also talk about the Swiss roll of Swiss roll mechanism. This is which is another method of it is basically an example of a dimensional reduction in 3D space. So we'll see that. Thanks a lot.